In this section, we're going to discuss we're going to start discussing a very important person in physics. I think he is one of the people that pushed physics to very, very great heights. Excuse me. I'm coming down with a cold, so forgive my voice if it becomes too rusty. So what we're going to do is we're going to start with Newton's laws of motion. So Newton was one very, very smart guy, I think in the 1700s. And he was super smart. In calculus, he came up with things like the laws of differentiation and things like that. Like he developed calculus itself because there's something that he wanted to calculate. I'm forgetting. I think he wanted to calculate gravity or something like that. But for him to do that, he needed to develop a new set of rules or a new set of mathematics, and he developed calculus, which is quite amazing. Newton's laws of gravity we are going to see later, but for now we're just going to look at Newton's laws of motion, and we are just going to state them here. So Newton, as smart as he was, I think he was around 24 or somewhere around that age. He developed a set of laws of motion. The first one says every body, so it says every body continues in its state of rest or uniform. So uniform, very important, or uniform motion in a straight line, unless impressed force acts on it. So basically what this is saying is, if I have an object on a table, I think right now you have things on your table, they're just going to remain there if no force acts on it. So imagine you're in a room that has no air, no nothing. That thing that you can see in front of your table, let's say your cell phone, that cell phone will remain there forever and ever. Amen. It will always remain there. It will never move because there is no force acting on it. And then he said it will remain in its state of rest, right? So this one will remain in its state of rest. But he also talked about uniform motion. So imagine there is a car moving at the same speed. It's not, the person is not pressing the accelerator, not pressing the brakes. And one important thing, this says unless an impressed force acts on it. For a car, it will be a bit difficult to imagine, but in space there is no force in space, right? So a rocket in space will just keep going. If you watch the movie Gravity, I would urge everyone to watch the movie Gravity by with Sandra Bullock. Let me write it down here. With Sandra Bullock and as we are physicists, everyone go watch Gravity if you haven't watched it. If you watched it again, as we are now physicists, let's watch it with a physicist mindset. If you watch the movie Gravity, they are let's say at the International Space Station. I think it was the International Space Station, and things got bad. But if you look at the movie, Sandra Bullock, there's a time when Sandra Bullock flew off that ship, and she could not come back because there was nothing to hold on to. There was no force, and she kept going in space. So in space, if you jump out of a ship in space, you keep going forever and ever. You will die. Of course, you die because you run out of oxygen and stuff. But your body will will freeze in space. And let's say you don't explode because of other things like it's a vacuum and stuff like that, but you keep going forever and ever, just going forever and ever until, I do not know, so many hundreds and thousands of years from now, you probably get into like a gravity field of another planet. But for our purposes in space, if you just if you push something, it'll keep going, because there is no other force that acts on it. On Earth, if you accelerate your car and you leave the accelerator and the brake, it'll eventually stop, because there are forces like air drag, that when you're moving in air, the air will help you stop, because you know how it is with air drag, air friction and drag and stuff like that, friction on the ground, those things are forces. But in a situation like space, where there's no friction, there is no drag, there is nothing, if you push something, it will forever go. That's a spoiler, man. Okay, spoilers, guys. Spoilers for the next 5 seconds. I'll write here when I'm done with my spoilers. I'll write here that spoilers are spoiler free now. Then you can switch on the headphones. But spoilers, that is how George Clooney dies in Gravity, because he pushed Sandra Bullock, and by pushing Sandra Bullock, we're going to see another Newton law of motion. He flew off. And because there was no other force acting on him, because in space there is no other force, there's no drag, there's no friction, he kept going and going and going and going and going. And then, yeah, that's how he died. Because he couldn't come back to the ship, he couldn't be stopped by any other force, because there is no force. So here, when you're watching Gravity, you'll be like, oh yes, a body continues in its state of rest or uniform motion in a straight line. Like he was moving in a straight line, flying away from the ship, unless an impressed force acts on it, right? So that is the movie Gravity. You need to go watch the movie Gravity. So let me write for those who switched off their headphones. Spoilers done. Okay, cool. So we have finished our spoilers for Gravity, right? Now let's go to the second law of motion. Second law of motion says the change of momentum per unit time. So some people can say change of momentum per unit time, or rate of change. Rate of change of momentum, because rate of change of momentum is change of momentum per unit time, is proportional to the force applied. Let me just say force applied and acts in the direction of the force. Or like to be more specific, acts in the direction of the straight line along which the force acts. Yep. So change of momentum per unit time, or rate of change of momentum, is proportional to the force applied, and acts in the direction of the straight line, acts in the direction of the straight line along which the force acts. We're going to see what this means later, but for now, let's just park it on the side and discuss law number 3. Law number 3 says action and reaction are equal and opposite. Another very, very important, all of them are important. This one is quite interesting because, guys, I'm starting spoilers again for that movie Gravity. So if you haven't watched it, switch off your headphones. I'm going to write spoilers done when I'm done spoiling Gravity, or explaining this concept of gravity, and I'll try to explain it with other things that don't involve spoilers. Okay, so I'm starting now. The spoilers. So in the movie Gravity, he knew that for Sandra Bullock to get to safety, he had to push Sandra Bullock, right? So by pushing Sandra Bullock, he himself was pushed back. So when he pushed Sandra Bullock towards safety, he was pushed away from that safe zone. because the force, let's say you pushed by 10 newtons, that same force was applied to push him backwards. That's why he now kept going backwards, because action and reaction were equal. His action was pushing Sandra Bullock, but the reaction was that he was pushed back by an equal and opposite force, and then he just flew off. You can see even on movies like Mars by what's this guy's name? That's another spoiler. If you haven't watched it, you know what to do with your headphones. By Matt Damon, I think it's called Mars, right? I think it's called Mars. So that movie, it's another one to watch. Watch it with a physics mind, like we are now. We are now physicists, right? Like, watch it with a physics mind. When he's going up in air and the guy flies to come get him, you can see when they are so, like, I can say, spraying out air. In space, you can actually maneuver using this. I don't know. It's spraying out air like your suit. Let's just say this is the space suit. Let's say this is your very special space suit. Like, this is your special space suit, right? These are your boots. So your space suit has these air vents that spray out air. When you press a button, they spray out air. Because scientists saw that so they spray out air like that. So it's like, because they know that if this air is pushing out with a force like that, you are going to be pushed to this side with an equal and opposite force. So if you want to go here, you press a button that pushes air on this side, and then since it's being pushed out with a force here, equal and opposite reaction says your reaction will be you go this side. And then if you want to maneuver, you can push air on this side, you go to this side. So that's how you travel, like going like that. So it's equal and opposite reaction, just applying Newton's third law of motion. So when you watch those movies, those space movies, and you see something like that, be like, nah, I know what they're applying. They're applying action and reaction. So now for the movies, spoilers done. Spoilers done. So basically that's what it says. So what this third law of motion just basically says is, if you're pushing a block of, let's say, a block of concrete here, that's you pushing a block of concrete. This block of concrete, if you're pushing it forward with the force of 10 newtons, this block of concrete is also pushing you back with a force of 10 newtons, right? And it is very, very, very important when it comes to this part. Where are you sitting right now? You're probably sitting on a chair, hopefully, or like a couch, whatever it is, wherever you are. This is you sitting down, right? I can't really draw, so pardon me. So this is you sitting. I can only draw stickman, except this guy in space, because I love space. But anyway, this guy, this is me. I'm sitting down and I'm recording these videos on my laptop, right? I'm sitting down. We all know that gravity is pulling me down. That one is obvious. Otherwise, I would be flying off. If gravity was not pulling me down, I would be floating. Like if you see people in space, in space stations or international space stations, they are always floating because there's no gravity there, right? But here on Earth, we have gravity and it's pulling everyone down. That's why we don't just fly off randomly, right? But why is it that we are not sinking into the ground? We know that gravity is pulling us down. Why are we not sinking? It is because of Newton's third law of motion. Newton's third law says every action is an equal and opposite reaction. So here, can you see? If I am stationary, like I am in my chair, I'm stationary, it is because gravity is pulling me down. Let's just give a random force. I'm not saying this is my weight, but I'm just giving a random force. Okay, this is actually close to my weight. My weight is close to like something like 610 newtons, right? Gravity is pulling me down with something around 610 newtons. I'm a skinny guy. So gravity is pulling me down with 610 newtons. But I'm not sinking into the floor. I'm not sinking into the chair and like struggling going into the floor. I'm not doing that. Because my chair where I'm sitting is reacting with a force that is equal and opposite. It is pushing me up with 610 newtons. It is reacting to this. because I do not have any motion, which means all my forces are balanced. So the action of gravity is being neutralized by the reaction of the chair that I'm sitting on. The chair is saying, dude, you're pulling this guy with 610. I'm going to push up with 610 so that he remains stationary, right? So this also has to do with the properties of the chair. Can it handle 610 and those kind of things, blah, 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 blah. But this chair can handle my weight perfectly, and that's what it's doing. It's pushing me up with 610 and then just neutralizing gravity. Action and reaction equal. So these are the 3 laws of motion by Isaac Newton, and I've tried to explain them better. If you haven't watched these movies that I used as examples, Gravity and Mars, please go watch them and then come back without switching off your headphones and go through this video again to see where I explained Newton's laws of gravity using those movies. If you're going to rewatch them again, watch them with a physics mindset. You will enjoy them even more. In the next video, we're going to just expand a bit on Newton's first law of motion and talk about something called inertia.
Created with free version for non-commercial use.